Hi, welcome to lecture 3.4 of the SAGE-based course on Monte Carlo methods. We're looking at conditional probability, random variables, loops, and conditionals. And the topic for this video is random variables. A random variable is a mapping from the sample space to the set of real numbers. In other words, it is a numerical value determined by the outcome of the experiment. This is not as complicated as it sounds. Okay, so let's look at a simple example. If we go back to our rolling two fair dice example, we know that our capital omega, or sample space, is here shown on the left, and let's take the random variable for this experiment to be the sum of the two numbers that appear in the sample space. The two numbers that make up the outcome, let's just add them and call that our random variable capital X. Clearly the sum is again another real number, so we are casting this sample space into the reals. That's okay, that's what we want. And then you get a mapping like this. So things like 2, 4, 1, 5, 3, 3, these set of 5 outcomes in orange get mapped to the real number 6 by our capital X. And these outcomes in light blue, 2, 5, 3, 4, and so on up to 1, 6. All of these get mapped to 7 and so on. Okay, so this mapping from capital omega to the real numbers is capital X, the random variable capital X. For example, we say the capital X of the outcome 6, 6 is 12. Okay, and the probability that X equals 12 is equal to the probability that we get the outcome 6, 6. Okay, because the probability that we get X equals 12 simply is the probability that we get the outcome 6, 6. And the random variable capital X of the outcome 3, 2 is 5. The random variable X of the outcome 3, 2, this guy right here, 3, 2 is 5. X of 3, 2 is the value 5 taken by the random variable capital X. That's what this means. So now let's look at the formal definition of a random variable. So let omega fp be some probability triple. Well, you should recall that omega is the sample space, script f is the collection of events or sigma field, and p is the probability whose domain is script f. And that's the probability triple. It's given to us. Then we can define a random variable on top of it, right? Then a random variable, say capital X, is nothing but a function from the sample space capital omega to the set of real numbers R. But it's not any old function, okay, that goes from capital omega to R. It's a function such that for every number little x, okay, every real number x in R, the inverse image of the half-open interval, right? The half-open interval that goes from -infinity to x, we look at that half-open interval in the range, okay, and we look at its inverse image under x, and we want this inverse image of the half-open interval right here to be an element of script f. So what is the inverse image of x for the half-open interval? It is nothing but the set of all little omegas that live in capital omega such that capital X of that little omega is less than or equal to x. Okay, so we simply pull back, look at the inverse image of the half line, and make sure that all the little omegas we get by pulling back, all the outcomes we get in the sample space whose x of omega is less than or equal to little x is actually an element of the sigma field. That's what we want our formal definition of a random variable to satisfy. So once again, given a probability triple omega fp, a random variable x is a function from the sample space capital Omega to the set of real numbers R such that for every little x in R, the inverse image of the half open interval negative infinity to x is an element of the collection of events script f. Okay, so mathematically this is what it means. Capital X is a random variable from omega to R. If x inverse of negative infinity comma x, which is defined to be the set of all little omega in capital Omega such that x of omega is less than or equal to x, is an element of script f, or the sigma field. Okay. What is a discrete random variable? A random variable is said to be discrete when it can take a countable sequence of values. Okay, remember that a finite set is also countable. The three examples below are discrete random variables we'll be seeing shortly. Now, how do we assign probabilities to random variables, right? We know about assigning probabilities to the collection of events. That sort of comes with the map. Now, how do we transform these probabilities assigned to outcomes in the sample space into these real numbers that these random variables take away from the sample space? So the way we do it is we assign probability to a random variable x in the following way. We say probability that capital X, the random variable capital X, takes a value less than or equal to the real number little x is given by the probability of the inverse image of the entire half line from negative infinity to that value little x. Okay, the same x here, right? So that's here. So we simply look at where all in the sample space capital Omega this half line maps to. That's what x inverse does. And then we look at the probability of that inverse image of the half line. And that's nothing but the probability of the set of all omega such that x of omega is less than or equal to x. Now, for probability to actually assign a value to a set like this in capital Omega, we have to make sure that this set is actually an element of script f, right? Because otherwise probabilities won't exist if this set itself is not an element of script f, or the sigma field, or the collection of events. Then we can assign probabilities to begin with. That's exactly the reason why our formal definition of a random variable explicitly mandated that the inverse image of the random variable actually produce sets in the collection of events, produce sets that are elements of the allowed collection of events. Okay, so that we can actually assign probabilities to these guys, right? This guy is the same as this guy, and as long as that guy belongs to the collection of events, we can assign probabilities to them, right? That's all that's going on here. Just chasing the definitions and making sure that we are able to do what we want in a consistent fashion. That's what most of mathematics is all about. Now, a new definition, the distribution function. The distribution function, or capital DF, also sometimes called the cumulative distribution function, or CDF, of any random variable capital X, is denoted by capital F. And what is this capital F? The distribution function capital F is actually a function of x. Capital F of x is simply the probability that the random variable capital X is less than or equal to its argument little x, the real number. And that is simply the probability of the event, the set of all omega such that x omega is less than or equal to x. So the distribution function capital F is defined for any x in the real line. Okay, so it's simply a shorthand for talking about the probability that the random variable x is less than or equal to x. That's all capital F of x is doing. Okay, let's look at these examples to sink in these ideas a bit deeper. So that's the sum of two dice example. So in our example above, we were tossing two dice and taking x as the sum of the numbers shown on the face of each die. So for example, we said that x of the outcome 3, 2 is the real number 5, but 3, 2 is not the only outcome that x maps to 5, right? That outcome that x maps to 5, because x inverse of 5 will give us all these guys whose sum is 5, which is 1, 4, 2, 3, 3, 2, and 4, 1. So now when we ask what's the probability that the random variable, this random variable, takes the value 5, then all we have to do is simply assign the probability taken by its inverse image in the sample space. Hopefully it's a collection of events. So that is the probability of the set of all omega such that x of omega is 5, which is nothing but x inverse of 5, which is nothing but the set 1, 4, 2, 3, 3, 2, 4, 1. And you already know how to calculate this, right? This should be 1 over 36 plus 1 over 36 plus 1 over 36 plus 1 over 36, which is 4 over 36. Okay. Example 2, pick a fruit at random. Remember our well-mixed fruit bowl from last week? So it contained 3 apples, 2 oranges, and 1 lemon. If our experiment is to take a piece of fruit from the bowl after really mixing it well, and the outcome is the kind of fruit we take, then we saw that the sample space capital omega was apple, orange, or lemon. Now we can define a random variable capital Y to give each kind of fruit a numerical value. For example, y of apple could be 1, y of orange could be 0, and y of lemon could be 0, right? So this random variable y is basically saying whether I got an apple or not, right? Now if I got an apple, it's going to give me the number 1. Say, well, maybe 1 stands for true or yes in some context, right? So that's all we're doing with the with turning the fruit bowl experiment into a random variable, or throwing a random variable on it. Now let's look at the third example. Flip until heads. Let's flip a fair coin until a head appears. Let capital X be the number of times we have to flip the coin until the first head. Right? So now capital omega is head. Well, the first toss we get a head, we stop. Right? Then the second possible outcome is T and H. So the first time we get a tail, the second time we get a head and stop. Or it could be T, T, H. We get 2 tails and a head. Or T, 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 H, or T, 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 H, or and so on and so forth, right? We could keep going. So of course, well, we could have, here we have a nice example of a countably infinite sample space, okay? So we actually have countably infinite possible outcomes in capital omega here. So x of h is 0, so we could simply let capital X, the random variable, be the number of times we have to flip. So here it's 0 because we got it right away. X of th is 1, x of tth is 2, 3, and so on. Alright, so here is a you try at home. So this is basically a homework. So please go through this example clearly. You have to think with some pencil and paper and try and fill these missing spaces. Please do watch this Khan Academy movie about random variables. I think it's quite interesting to get perspective from Salman Khan, as well as my fairly more formal perspective in this class. So when we introduced the subject of probability, we said that many famous people had become interested in it from the point of view of gambling. Galileo was one of those who wrote about dice, including an important piece which explained what many experienced gamblers had sensed but had not been able to formalize. That is the difference between the probability of throwing a 9 and the probability of throwing a 10 with 2 dice. You should be able to see why this is the case from our map above. If you are interested, you can read a translation of Galileo's, but this is something for you to take a look at, something translated from 1898. This is also printed in a nice book called Games, Gods, and Gambling by F.N. David, originally published in 1962. Those are some distractions for you to indulge yourselves in if you're bored. Now, please go through these U-tries on your own, example 1, and read them carefully, and also go through example 2. And this is a good time to pause the video, and we'll start with indicator functions for the next video.